Hello everyone, this is the 7th week class. Today we are going to do two things. First one is to study a technique called logistic regression, and the second one is to study comparing two regression models in terms of whether the R-squared difference is significant, right? So let me talk about logistic regression first, right? So basically, logistic regression is used when we have a categorical dependent variable. Let's try to understand this. Suppose we have a equation like this. So this is the regression equation. For the regression, right? This one, the dependent variable, should be always quantitative variable, right? And these ones, the independent variables, these can be either quantitative or qualitative, right? So it can be a categorical variable, right? So what happens if we have a qualitative variable for the dependent variable? If y is, right? If this one is qualitative, right? Then we cannot use the ordinary regression, right? If this is so, then we need to use a different technique, which is called the logistic regression, right? So logistic regression is used when we have a categorical dependent variable, right? Today, we are going to study a specific logistic regression in case where we have two categories, right? In that case, the logistic regression is called the binary logistic regression, right? So binary logistic regression is a type of regression analysis where the dependent variable is a dummy variable, which is coded either 0 or 1, right? Let me talk about why we cannot use ordinary regression analysis for the case where we have a categorical dependent variable, right? Suppose we have a data like this. Since dependent variable is binary, that means it can be either 1 or 0, right? So suppose we have a data like this. Then if we use an ordinary regression line, like a red line here, then we cannot say that the red line is a representative of the data points, right? So in this case, we should have lines like this, right? So that the line can correctly represent these data points, right? That's why we need to have a curve instead of a straight line, right? For the logistic regression, we don't directly use the y values. As I said, the y value is 0 or 1, right? In case of a binary. Instead of using those numbers, we use some kind of a probability, right? In this case, I use a p here. P represents the probability that y is equal to 1, right? Obviously, 1 minus p represents the probability that y is equal to 0, right? This one is a natural log, right? This one is called the logit, right? In logistic regression, they use this model and they try to find these values just like the ordinary regression line. they find the slope and then intercept, right? In case of a logistic regression, when we predict by using the logistic regression model, we don't actually predict the y values. We compute the p values, right? Once we get the alpha and beta in this case. And if p is close to 1, we can say that the y is equal to 1. And if p is close to 0, then we can say that y is equal to 0, right? That's the basic idea here. Here I am showing you the process of getting p here, right? So you know that the natural log, right? So natural log is basically, natural log is the same as log e, right? So I'm showing you the how to transform, these ones to basically p is equal to this one, right? So once you get the alpha and beta, right, you plug in here and you get p, right? So if p turns out to be, actually we are using this criterion. If p is greater than 0.5, right, then y is equal to 1, and p is less than 0.5, y is equal to 0, right? So this is the summary of the logistic regression model. As I said, p is the probability that y is equal to 1. And p over 1 minus p is called the odds ratio. And if you take the natural log of odds ratio, it is called the logit, right? Once you get the alpha and beta value, you can get the p value. In this case, p value is not the one that we use for the hypothesis testing, right? This is just p is a probability, right? So if p is greater than 0.5, then y is equal to 1, right? Well, let's talk about method of getting alpha and beta, right? In case of the ordinary regression analysis, we use the least square method, right? But in case of a logistic regression, we use the method called the maximum likelihood, right? So I'm going to talk to you about how to get the alpha and beta, right? The maximum likelihood method is just like the least square method, right? It's a kind of a method for estimating the coefficients, right? So they create some kind of a likelihood function, right? I'll talk about this one by using the example, right? And then you want to make this likelihood function as large as possible, right? So in this case, you want to find the coefficients alpha and beta that makes the likelihood function as large as possible, right? So let's try to understand this method by using an example, right? Suppose you have data like this, right? Okay. And then for a specific set of regression coefficients, I mean the alpha and beta, right? In this case, since we have 3 independent variables, then we need to find the beta 0, beta 1, beta 2, and beta 3, right? So for a specific set of regression coefficients, we compute p and 1 minus p, right? Okay. And then, so for every set of regression coefficients, you find the p and 1 minus p, right? And then you want to find 1 one specific set of regression coefficients, which makes the likelihood function the largest, right? So in this case, the maximum likelihood function is simply, since this one is y is equal to 1, so you take this one, right? And in case of this, we take the 1 minus p here, right? And this one is 1, so you take this one. So you multiply, these things, right? So you want to make the product of these things, right, the largest, right? So you want to find the a specific set of regression coefficients which makes this product the largest, right? That's the solution. So we are going to actually use actual data for finding the coefficients for the logistic regression. Once we get the output, we need to interpret the output, right? So before we go into the output, let me briefly explain the outputs, right? Once you get the beta is different from the beta we saw in the ordinary regression, right? So in this case, you need to take the exponential, right? So once you get the beta, right, you take the exponential, right? And just like the ordinary regression, we need to do the hypothesis testing, right? So for the coefficients, in case of logistic regression, they create some kind of word statistic, and the interpreting the p-values for the logistic regression is same as the ordinary regression output, right? So if p-value is less than alpha, right, then you reject null hypothesis. In this case, null hypothesis is what? The coefficient is not significant, right? So if you reject null hypothesis, that means what? The coefficient is significant, right? And for the overall model fitness, you use the these things, right? And these ones, right? This r square is the same as the r square we saw in the ordinary regression, right? So bigger r square means what? Your model is better, right? And this one, this is a little bit strange because in this case, your model is good if p-value is greater than alpha, right? Usually, model is good if a p-value is less than alpha, right? In this case, it's a special case where the model is good if p-value is alpha, right? Because in this case, the null hypothesis is actual is equal to predicted for the dependent variable, right? So that means if you reject this one, right, then your model is not good, right? So you should not reject null hypothesis in this case. So that's why the model is good if p-value is greater than alpha, right? Now let's go to actual example and then let's get the output and try to understand the output, right? So let me show you how to do the logistic regression, right? So we are going to use in this case, the hiring as the dependent variable, and education and experience and gender are the independent variables, right? So the education means the years of education, and the experience is also the years of experience. And So you want to know whether the years of education and years of experience and their gender affects the hiring, right? So you go to the analysis, right? And you go to the regression and you take the binary, right? Logistic regression, right? And then you move hiring to the dependent variable and the education to the independent variables, right? And you get the output here, right? So you get the p-values for the independent variables, right? And you get the here the r square, right? So it's very simple, to do the logistic regression, right? I'll try to show you how to interpret these results, right? So this is the output for the logistic regression, right? So in this case, R square is 0.724, slightly low, right? And this one is p-value is 0.579, means this one is greater than alpha, right? So as I said, this is special case, right? If p-value is greater than alpha, that means your model is good, right? And these ones are the p-values for the coefficient, right? So in this case, education year, in this case, greater than 0.05, right? So education, years of education doesn't affect the hiring, right? So how about the years of experience? Years of experience in this case is less than 0.05, right? So you reject null hypothesis. That means years of experience affects the hiring, right? How about the gender in this case? Gender also, in this case, p-value is less than 0.05, right? So that means you reject null hypothesis. So that means gender affects the hiring, right? If you look at the these ones, by using the regression results, your model predict your model's accuracy is about 89.3%, right? So in this case, if you want to actually predict, you need to write an equation like this, right? P is equal to, right, 1 plus E2, right? So in this case, negative 14.248, right, plus 1.155 x1 and plus 0.910 x2 plus 5.604 x3, right? So once you have the values for x1 and x2 and x3, you plug in here and you get the p, right? As I said, if p turns out to be greater than 0.5, you classify the hiring as 1, right? So if p is less than 0.5, then, so in this case, y is equal to 1, right? This is y is equal to 0, right? Now let's talk about another topic, right? So in this case, we are going to compare regression models, right? In terms of the R square difference, right? So you want to know which each model is a better one, right? So in this case, we have to think about two cases. One is the nested model case, and the other one is non-nested model case, right? So let's talk about the nested model case first, right? So what is the nested models? In order to understand what the nested model means, right? Let's look at the here model 1 and model 2, right? And here, so in this case, in model 1, we have three independent variables, right? If you look at model 2, x1 and x2 are the same as the ones in the model 1, right? The only difference is that x3 is removed from model 1, right? This kind of situation is called the nested models, right? So we are going to compare in terms of R square, right? So if you run this one, you will get R square, right? Model 1. And you will get the R square for the model 2, right? You want to know there is a difference, right? In terms of its significance, right? It will be a difference, right? But you want to know whether the difference is significant, right? So we are going to do this analysis by using SPSS, right? The basic idea is that you are going to remove x3 from model 1, and then you are going to do the significant test for R square change, right? So I'll show you this, but let me talk about the process first, right? So you go to the analysis and you take the regression and the linear. So you move y to the dependent variable box, and you move x1 and x2, x3 to the independent variable box, right? And then you click next, right? This is the critical, right? I'll show you this when we do the actual example, right? And you will get the another screen if you click the next. And then you move x3 to the independent variable box, right? And then you have to select remove, right? Below, right? And then you click statistics at the right, and then you select estimates, model fit, and the R square change, right? And the for the output, right? You need to look at the p-values of model 2, right? If p-value of model 2 is less than alpha, right, then R square change is significant, right? This means that adding x3 is significant, right? So that's the basic process, okay? So let me show you how to compare models, nested models, right? In this case, I'm going to use a case where we have only two independent variables, right? So we have here y and x1 and x2, right? And then I'm going to try to remove x2 from this model and then compare two models, right? So let's go to the analysis, and you go to the regression and linear. Okay, so this is the I already moved y to the right and x1, x to the right, and then you click the next, right, and then you move x2. In order to remove x2, you click this one, and then you select remove here, right? Okay, and then you click the statistics, and you click these things, right? And you click the R square change, right? And you click this one, and you click this one, right? So if you look at the output, right? Here the important output is this, right? So in this case, you look at the p-values here, right? So since this p-value is less than 0.05, right? So that means the adding x2 is significant, right? Right? That's the basic process of comparing two models, right? Now let's talk about the comparing non-nested models, right? So in order to understand what the non-nested models mean, let's look at these ones, model 1 and model 2. So we have the same y's, right? But we have a different independent variables, right? So in this case, independent variables are completely different, right? But we can think of another case where we have x1 and x2, and for model 2 we have x1 and z2, right? Even if in this case, one independent variable is in both models, but second independent variables are different, right? So this type of situation is called non-nested case, right? So in this case, the little bit complicated for the analysis, right? In this case, the basic idea is to use the Hotelling's t-test, right? So in order to do this, there is no process for doing this test. You have to do it by hand, right? In this case, so you need to compute R1 for model 1. Actually, this one is easily obtained if you do the regression for model 1, right? So the R is simply the square root of R square, right? So this one is very easy to get, right? And then you get the R value for model 2, right? So you do the regression for model 1 and model 2, you get the R values for each case, right? And another thing that you need to obtain is to get the R3. This is the critical part here, right? So in order to do this, you need to get the predicted value of y for each of these two models, right? So this is the critical part. You need to get the predicted value of y for model 1 and the predicted value of y for model 2. And then you need to do the correlation analysis, right? So you need to get the correlation coefficient, right? Once you get these numbers, right, you need to compute t, right? This is called Hotelling's t, right? Using this very complicated thing, right? And this one should be go here, right? Square root of these things, right? And once you get this t value, so if the t is greater than 1.96, you reject null hypothesis, right? So in this case, null hypothesis is what? R1 is equal to R2. This means that R change is significant, right? You are rejecting this, right? So there is a difference, right, in terms of R change, right? Let me show you how to get the predicted value for y. So you go to the analysis, and you go to the regression, and you go to the linear, right? And let's say let's remove this one and this one and this one. So you move y to right and x1, x2, right? In order to get the predicted value for y, you go to the here, right? And you select this one, right? Okay. And you continue. And you click this one, right? So if you do this, you will get the R value for the first model, right? So this one is the predicted value, right? If you look at the data, you have a new variable is right, is shown here. This is the predicted value of y for first model, right? So let me go to again linear. So you do the regression, right? So here in this case, R is 0.897, right? And then you get the so predicted value for the first model, right? Here, okay. So once you get the predicted value of y for model 2, right? So you will get another, predicted value, right? And then you need to do the correlation analysis, right? So in this case, you do the correlation, and this one, you take this one, and you move predicted value to the right, right? And you move the predicted value of y for model 2 to the right, and then you click this one, right? So you get the correlation coefficient, right? In our case, I don't have another model, second model for this analysis, so that's why I cannot show you how to do this correlation analysis, right? So this is the way to get the correlation coefficients, right, for the predicted values. So we are back to PowerPoint. I showed you how to get the correlation coefficients, right? So you do the regression for model 1, right? And then click save at right, and then you check the unstandardized on the predicted values, and you will get the new variable, right? And you do the regression for model 2, and you go through the same process, right? You get the predicted value of y for model 2, and then you do the correlation analysis for predicted values, right, to get R3. Once you get R3, you compute the Hoteling's T, right? If T is greater than 1.96, you reject null hypothesis, right? So that's the process of comparing non-nested models, right? So that's it for today's class. See you next time.